So every graph has, so today we're looking at normal distributions. And like we saw last time when we graph a histogram and we graph more and more and more bars, it starts to look more like this bell-shaped curve. And this is called a normal distribution. And it's really useful for solving a lot of application problems. Now every normal distribution has a mean. Okay? The mean is just the average value. So that would be the x value. In this case, the mean is 80. It's just the middle point. And it has a standard deviation. And the standard deviation tells you how skinny the normal is. So a really small standard deviation would be a really tall and skinny normal graph. And a really big standard deviation would be a really wide and fat normal graph. So this has a big standard deviation. This one has a small standard deviation. Okay? And changing the normal would just move the graph side to side. Changing the mean. The graph is bell-shaped, symmetrical about the mean. Okay? If you change the mean, then the graph will be shifted left or right. So a small mean would be over here, and a big mean would just move the graph over. Okay? And the standard deviation causes the curve to become broader and narrower. So a broad curve has a big standard deviation, and a narrow curve has a small standard deviation. The area under the curve is always 1. This represents 100% of the probabilities. Okay, so the area under a curve of a normal distribution represents the probability within that range. There's a 68, 95, 99 rule, which is that about 68% of the population are within 1 standard deviation. So what that means is that if I take my graph and I go 1 standard deviation, 1 sigma, left and right from the middle, that the area under that part is about 68% of the total area. 95% of the population are within 2 standard deviations. So if I go across again, another standard deviation, you can see that I've pretty much got the whole area under the graph by that point. There's only a very small amount, 5% left. And 99.7% is within 3 standard deviations. And you can take a look at some of the pictures of normals on page 539 in your text. Now the terminology, or the way that we write this, is we say that if x is a normal distribution, we write x is distributed as a normal graph in brackets. We write the number that represents the mean first, and then write the standard deviation squared second. The standard deviation squared is also known as the variance. So remember what the standard deviation is? You have to
Also root mean squared.
It's root mean squared, right? You have to find the average and then take away the average from all the points to find out how much difference there is, and then square all those differences, and then add up all the differences. And it was a complicated process, but we could use the one variable stats to actually find that using the graphing calculator. You don't ever have to go through that process. But just know if standard deviation is small, then all the data is really close together. And if standard deviation is big, then the data is really spread out. Okay, so for example, let's say we've got a company that has figured out that the lifetime of a car battery is normally distributed with an average of 48 months life. It means car batteries last 2 years. And the standard deviation is 8 months. So let's just sketch a graph of what that normal curve would look like. I just draw a nice bell-shaped curve like the one above. Come on. And where is the midpoint? the tallest point, which is the mean. Okay, so the mean is right in the middle. Now, to find out where one standard deviation is away, you can kind of look at the graph on the back, and it draws those lines right on the normal graph that represent 1 standard deviation, 2 standard deviations, and 3 standard deviations. So there's my 48 months. 1 standard deviation would be about here. So there's my first standard deviation. And that standard deviation is 8 months. So after 8 months, 56 months, I've got about 68% of the data within those 2 bars representing 1 sigma away from the mean. And 8 months lower would be 40. So between 40 and 56, I've got about 68% of the data. If I go over 2 sigmas, it's about here. That would be another 8 months. So another 8 months after 56 is 64, or 32 on the low end. And then by the time I hit 3 sigmas, I've pretty much covered the whole graph. This graph does actually continue on in both directions, but it's so close to the x-axis that there's pretty much no area underneath it. So 3 sigmas would be another 8 months later. So 72 months and 24 months. So even without knowing any information or having a calculator available, we can actually estimate how much of the car's battery is below 56 months. So we've got 68 in here. And then we have 95 if we went to here, 99% if we went all the way to the end of 3 sigmas. So you can actually see the percentages written on the back. If you go from the middle to 1 sigma, that's 34%. And if you go from the middle back 1 sigma, that's also 34%. Okay, so altogether you'd have 68% in between the first 2 bars. Okay, and the next one is 14%, 14%, and 2%, 2%. Okay, and that's true for every normal. Every normal graph has about 34% in each of these sections, about 14% in each of these sections, and about 2% in each of these sections. So what percentage of the batteries have a what percentage of the batteries have a lifetime less than 56 months? 68 plus 14 plus 2. Approximately 84%. Okay. Or you could think of it as the left-hand half is 50% of your graph, and then you're just adding another 34. So 50% plus 34 is 84. So if we want to draw that as a picture, we could say we're trying to find out what is the area under the graph from 56 to the left. And the total area represents the total probability. What percentage of the batteries have a lifetime from 56 to 72 months? From 56 to 72. About 16. How did I get that? Well, I know that this represents 1 sigma, and this represents 3 sigmas. So I'm going from this part to this part. It's exactly the opposite of the 84%. 100 minus 84%. Technically, I should say 99.7 minus 84%. And what is the approximate range? What's the smallest lifetime for a battery? So how many months does a battery usually last? 48 is the usual. So a battery usually lasts 48 months. Most of the batteries are going to be between 40 and 56. Where's the beginning of that normal graph? About 24. So you can take the average and minus 3 sigmas. So take the average, take away 3/8, and you get 24. That's the smallest value. And you can take the average and add 3 sigmas. So take the average and add the standard deviation 3 times, and that'll be approximately the largest value. So the range is about from 24 to 72. Are there any questions? David? Any questions? Okay, so on the second page, I'm asking the question now, what if we wanted to find out how long they last between 48 and 54 months? Like, what's the percentage of batteries that have a lifetime from 48 to 54? Yeah. Oh, this is an approximate range. So what if we want to find like half a sigma or a couple thirds of a sigma or just any random range? This is where the graphing calculator becomes really helpful, and we'll use something that's called the standard normal distribution. The standard normal has an average of 0 and a standard deviation of 1. So we can pretty much take any normal distribution and just move it so that the average is right on the y-axis and the standard deviation is 1. It's symmetric about the average, and the total area under the curve is 1. And the horizontal axis is measures like the standard deviation. And what we say is that the standard normal can be written as, we especially use the letter Z for standard normal, and we say that it's distributed as a normal. And remember, the first number represents the mean, so the average is 0, and the second number represents the standard deviation squared. So 1 squared is 1. Okay, so then when x is equal to 1, that x represents 1 standard deviation. X is 2 represents 2 standard deviations. So this would be the standard normal graph. This would be x is 0, x is 1, x is 2, and so on and so forth. So quite often they'll ask us the question like, what's the area between negative 1.3 and 2.1? So what's the area from this part here to this part here? And we could approximate that. It's about 68 plus 14. It's about 82. But we can actually find it out exactly and have the calculator draw a pretty picture for us. So I'll show you how to do that. So first of all, you need to clear all of your statistical plots and all your equations, all the things that we did last time. So if you go to your stat menu, or list, wait, where is it? Stat, clear list, so number 4. Clear my list. I'm going to take my stat plot and turn my plots off. I don't think you have to clear your list as long as you turn your plots off. To turn your plots off, you go to the yellow button and then y equals. And then you have some plots here and just hit enter, and instead of choosing on, go on to off and hit off. Or you can go up here and just hit enter on top of the, if your plot 1 is black, that means it's on. If you hit enter on top of your plot 1, that'll turn it off. That should be enough. I'll clear out my other functions. Then go to your window and change the window from negative 4.7 to 4.7 for x with a scale of 1, and from negative 0.15 to 0.5 with a scale of 0. Let's just do scale of 1. Oh, no, it would have to be like 0.1. Doesn't really matter what the scale is. Point 1. So now go to your catalog, second 0, and choose S right beside the 4, and go down to shade normal. There it is, shade normal. And the first thing that we plug in is this lower bound, negative 1.3, and then comma, and then the upper bound, 2.1. So shade. So what I typed was shade normal, and then the lower bound, comma, upper bound. And then you hit enter. And it's really fun. It colors it for you, and it gives you the area. The area is the probability, 0.885.
How would we do it without going to
I don't know.
okay.
If you want to find the area to the left of 1.57, you can do shade normal, and then choose a really small number, like negative 99. Turns out that negative 5 is sufficient. And then the largest value. If you try to graph this, nothing happens. So I go to my graph again. I do second enter so I don't have to search for this in the catalog. Negative 99, 1.57. I graph it, nothing happens. So what you have to do is after you've graphed something, you actually have to clear the drawing. So you go to your draw menu, second program, and you have to clear drawing. Choose number 1. So second program, clear drawing. Second program, clear drawing. And then you can type in your equation and it'll dry. So it colors it all, and it gives you the percentage, 0.942. So you clear drawings between second program, clear drawing, and then you can hit, now my calculator's taking a long time to think. So then you can hit second enter so you don't have to go back to the catalog again and try to find this expression. Here's another way to do this as well that doesn't draw it for you, it only finds the numbers. So I'll show you how to do that as well. I like the drawing part because it helps connect this to like a visual understanding. 2.45 all the way up to 99. So going from negative 2.45, it's almost all the area. You can only see like one little white dot on the left side. It's 99.3% of the area. Okay, so for example 2, it's just different terminology, same question. It's asking you to find the probability from negative 2 to 1 under the normal curve. So you could do this by doing shade normal from negative 2 to 1. But you can also use the normal CDF function. So with the normal CDF, you need a couple more arguments. You need -2, 1. You also need to give it the average, the mean, which is 0, and the sigma squared, which is 1. And the nice thing about this one, it'll graph any normal curve, not just the standard normal, but even if the normal has a different mean and a different sigma squared. So again, all these things can be found in the catalog. Second 0. Yeah. So the 0 represents the mean of a normal curve, and the 1 represents the standard deviation squared. So you'll always have to put in the 0 and 1 with the normal CDF. That's written right here. You'll always have to put those in. The shade, that's what's nice about the shade normal. You only have to put in 2 numbers. So, yeah, the normal CDF doesn't draw it for you, but it will calculate the total probability. Well, let's see, maybe it doesn't need those numbers. Oh, it doesn't need the 0, 1. So if you don't put the 0, 1, it just assumes that you're looking at 0, 1. Yeah, for most questions we're looking at a standard normal, where you have a mean of 0 and a standard deviation of 1.
Will they tell you it's a standard normal?
For sure. To tell you it's a standard normal, usually they write it like this, which seems really kind of like a crazy way to write it, but this expression means this is a standard normal. That's right. Okay, so that is 82%. So the chance that z is less than 1, you can do second enter to get that back again. So we want to go from some large negative number all the way up to 1. And you get 84%, just like we saw on the first page. So from -99 to 1 is 84%. Okay, so you try the last 3. Okay, so the probability that z is bigger than -1.5, we take -1.5 as a low bound, 99 or something like that as a high bound, and we get 93%. Z is less than 0, you can do without doing any calculations at all. It's half the graph, because 0 is the mean. So this one will be 50%. Now z is greater than 0.8. The absolute value means that either z is greater than 0.8 or z is less than -0.8. So we're looking for 2 parts of the graph, from 0.8 or -0.8. Either this section or this section. So since the graph is so nicely symmetrical, it's even on both sides, you could just find one of the halves. So maybe I could find the negative half and then times it by 2. So to -0.8, I get 21%. So I'm finding the normal CDF from -99 to -0.8. That was 21%. So probably the other side will also be 21%. So times it by 2, and I get 42% of the graph. And I could check that by doing another calculation from +0.8 all the way to 99. Yeah, it's the same. So your practice for today comes from page 451, numbers 1 to 7.